All right, hello and welcome. If you're a physics student, you know this book, Irodov's Problems in General Physics. It's the stuff of legends, right? Famous for its super tough problems. Today, we're going to tackle one of its classic mechanics questions. I'll walk you through it step by step, so you can really get a feel for how to break down these tricky problems.
But before we dive into the numbers and the buggies, let's zoom out for a second. Have you ever thought about what connects everything, from galaxies crashing into each other to a simple man jumping between two buggies? I mean, we're talking about totally different scales, but there's one single elegant law that governs every single one of those interactions. Any idea what it is?
You got it. It's the law of conservation of momentum. This law is basically the hero of our story today. It's our superstar. So what does it actually say? Well, in a nutshell, if you have a closed system, meaning no sneaky outside forces are messing with it, the total amount of motion before something happens is exactly the same as the total amount of motion after it happens. It just doesn't change. Yeah, momentum can get passed around between objects, but the grand total, it stays constant. And this single idea, this is the master key we're going to use to solve this problem.
Okay, so let's introduce the challenge for today, the famous buggy problem.
And here it is, problem 1155, straight out of Irodov. Let's read it real quick. Two identical buggies move one after the other due to inertia, with the same velocity v0. A man of mass m rides the rear buggy. At a certain moment, the man jumps into the front buggy with a velocity u relative to his buggy. Find the velocities with which the buggies will move after that. So our mission is to figure out how fast each of those buggies is going after the man does his jump.
Okay, let's break down the initial setup. What's the scene before all the action starts? Well, we've got two identical buggies, each with a mass of capital M. We've got our guy, mass little m, just hanging out on the rear buggy. The whole system, man, buggies, the whole shebang, is moving along at a steady speed v0. And, super important, we're told there's no friction. That's good news for us, makes the math a lot cleaner.
All right, now before we jump into the equations, let's talk about the big one, the classic trap. This is the spot where almost everyone gets tripped up the first time they see this problem. But don't worry, once you see it, you'll never fall for it again.
So the problem throws us a bit of a curveball. See, it gives us the man's jumping speed, which it calls u. But here's the catch. That speed is relative to the buggy he just jumped from. And that's a problem for us. Why? Because our big hero, the law of conservation of momentum, it doesn't care about relative speeds. It needs the real speeds, the ones you'd see if you were just standing still on the ground. So that's the million-dollar question. What is the man's actual velocity relative to the ground?
And this right here is the absolute heart of the problem. You've got relative velocity, u, that's the speed the man feels as he's jumping, but then you have the absolute velocity, let's call it v-man, and that's what someone standing on the ground would clock him at. The problem gives us u, but our equations demand v-man. If we mix these up, we're toast. We have to use the absolute velocity for our momentum calculations.
So how do we get from one to the other? Luckily, it's pretty straightforward. It's just a simple addition. The man's actual velocity relative to the ground is whatever the new velocity of the buggy is, we'll call that v1, plus his jumping speed u. That's it. v-man equals v1 plus u. This little formula is the key that's going to unlock this whole thing for us.
Okay, the trap has been spotted, the bomb has been defused, we are ready to actually solve this thing. Now the best way to handle this is to break it into two separate events. Part 1, the man jumping off the rear buggy. And we're going to follow a really simple three-step process. First, define the system. For this first jump, our system is just the man and that rear buggy. Step 2, apply our trusty law of conservation of momentum. And step 3, do a little algebra to solve for what we want, which is the rear buggy's new speed, v1.
So let's look at the before snapshot. Right before he jumps, what's going on? Well, the rear buggy and the man are basically one big object. They're stuck together, so their total mass is just capital M plus little m, and they're both cruising at speed v0. So initial momentum, easy peasy. It's just their total mass times their velocity.
Okay, now for the after snapshot. The instant after he pushes off. What do we have now? The buggy, mass, m, has a new speed, v1. And the man, well, here's where we use our key. His velocity isn't just u. Remember, it's the buggy's new speed plus his jump speed. So his velocity is v1 plus u. Don't forget that.
And now for the magic. Our law says before equals after. So the initial momentum, that m plus m times v naught, has to be equal to the total final momentum. That's the buggy's momentum, m times v1, plus the man's momentum, which is m times that whole quantity, v1 plus u. And boom, that equation right there is everything we need for the first half of this puzzle. All right, part 1 is done. We've handled the jump. Now for part 2, the landing. Our guy is flying through the air and he's about to land on the front buggy. Let's analyze that.
And guess what? We're going to use the exact same 3-step process. No need to reinvent the wheel. Step 1, define the system. This time it's the man and the front buggy. Step 2, apply conservation of momentum to the collision of him landing. And step 3, solve for the front buggy's final speed, which we'll call v2.
So what's our before picture for this second event? It's that split second right before his feet touch the front buggy. So what's moving? The front buggy is still just minding its own business, cruising along with its original momentum, m times v naught. And our man is still in the air, carrying his momentum, which we already know is m times that big quantity, v1 plus u.
And what about the after state? Well, he lands on the buggy and they stick together, right? In physics speak, that's a perfectly inelastic collision. They become one unit. So their combined mass is, once again, m plus m, and they move off together with some new final speed, v2.
So you know the drill. Before equals after. The initial momentum, that's the buggy's mv0 plus the man's mv1 plus u, has to equal the final momentum of the combined man-buggy system, which is m plus m times v2. You see how cool this is? We can just chain these events together using the result of the first one to set up the second one.
Okay, the physics part is officially done. We've built our 2 big equations. Now it's just a matter of rolling up our sleeves and doing a little bit of algebra to find our answers. Let's start with v1, the speed of that rear buggy.
So remember our first equation? Let's solve it for v1. First thing, let's distribute that little m on the right side. That gives us mv1 plus mu. Okay, now let's get all the v1 terms together. We can factor out v1 and we're left with m plus m times v1. We want to get v1 all by itself, right? So let's move that mu term over to the other side by subtracting it. The very last step is just to divide by m plus m, and there we have it. And you know what? This makes total sense. The buggy started at v0, and now we're subtracting a little bit. Of course it slowed down. The man had to push off of it to go forward, so it gets a little kick backward. That second term is basically the recoil.
Now for v2, the speed of the front buggy. Okay, this one's a little bit more of an algebra beast, but the idea is simple. We take that big expression for v1 we just found, and we plug it into our second equation. Yeah, it's going to look messy for a minute. You'll have to expand everything out and group all your terms together, but trust me, if you're careful, a bunch of stuff cancels out really nicely. And when all the algebraic dust settles, you're left with this beautiful final answer. And once again, check your intuition. The buggy started at v0, and now we're adding a small term. It got faster, which makes sense because the man landed on it with extra forward momentum, giving it a little push.
So let's wrap this up. What are the big lessons here? First, always define your system clearly before you start. What's interacting? Second, never forget the relative velocity trap. That's the #1 pitfall. You always need velocities relative to the ground. Third, just trust the law. Conservation of momentum is your best friend in these problems. It always works. And finally, probably the most important strategy. Take a scary, complicated problem and break it down into smaller, bite-sized pieces. That's how you conquer physics.
So there you have it. You've now seen how to master this classic Irodov problem. But if you really want to prove to yourself that you get it, here's a little challenge for you. What would change if the man jumped backwards instead of forward? How would that affect the u in our equations? Just think about the signs. Go ahead, try working through the math. If you can solve that, then you've absolutely got this down.